Hi guys, in this lecture we will look at some of the problems that are based on DC machine. These kind of problems can be asked in the GATE examination. So first kind of problem that we will be looking at is based on induced EMF in a DC machine. It is irrespective of generator or motor, the induced EMF remains the same. So what is the expression for induced EMF? E is equal to phi n Z by 60 into P by A. What do various terms represent here? E is the EMF, phi is flux per pole, Z is number of conductors, N is speed in RPM, then P is number of poles, and A is number of parallel path. Now what is this concept of parallel path? So number of parallel path are equal to number of pole for lap winding, and it is equal to 2 for the case of wave winding. Is it fine? Now what does number of parallel path represent? When we are connecting the coils, some conductors will be connected in series and some will be connected in parallel. So the total number of parallel connections that are formed are known as the number of parallel path. Suppose I have 100 conductors. I divide them in 4 groups of 25 each. Now these 4 groups are connected in parallel, which means number of parallel path is equal to 4. So that is a describing factor when we talk about induced EMF, as well as when we talk about the armature resistance of a DC machine. Now let us take a look on how this problem can be solved. It is saying the armature of a 2-pole 200 volt generator. So this 200 volt is basically terminal voltage. Has 400 conductors. So Z is 400. Runs at 300 RPM. N is 300 RPM. We need to calculate the useful flux per pole. So this is 200. I am assuming at no load. At no load, terminal voltage is equal to induced EMF. It will be equal to flux per pole into speed into Z by 60. Since it has 2 poles, there can be at most 2 parallel paths, because even for a lap winding, P is equal to A, that is 2. And for wave winding, A is already 2. So flux will come out to be 0.1 Weber. Now it is saying what is average value of EMF induced in each coil on breaking the field. Breaking the field means if you open circuit the field winding, what is the EMF induced? Now EMF induced is equal to N d phi by dt. When we open circuit the field winding, the flux will be reduced to 0. As the flux is reduced to 0 in how much time? 0.1 second. What is the number of turns per coil? 1200. What is the change in flux? 0.1 Weber. Time is 0.1 second. So it is 1200 volt. Is it fine? So that much EMF will be induced if we break the field winding. In the next problem it is saying a 1500 kilowatt 550 volt 10 pole generator runs at 150 RPM. What must be useful flux per pole if there are 2500 conductors lap connected? Full load copper loss are 25 kilowatt. Now see, here I know about the power output 1500 kilowatt. What I also know is the terminal voltage 550 volt. Based on that, what I can find? Armature current 1500 into 10 to the power 3 by 550. How much will it come out to be? 2727.27 ampere. Okay. Now I also know the full load copper loss. I know copper losses are equal to Ia square Ra, which means RA will come out to be how much from this equation? 3.361 milliohm. Okay. Now, from this finding, why I have found RA actually is so as I can determine the induced EMF. Now, the performance equation of a DC generator is EMF is equal to terminal voltage plus voltage drop. So, what is terminal voltage? 550. What is voltage drop? 2727.27 into 3.361 into 10 to the power minus 3. So this comes out to be 559.2 volt. Now once I have induced EMF, I can find out the flux. Flux will be EMF upon NZ A by P. Okay. Now EMF is how much? 559.2 by speed is how much? 150 RPM. E into 60 will also be there. And number of conductors are 2500. Now P will be equal to A because it is lap connected. So from this we can derive that flux is 0.0894 Weber. Okay. Now once I know about the flux, it is saying that the flux density is 0.9 Weber per meter square. So area is 0.0894 by 0.9, which means 0.0994 meter square. So that will be the cross-sectional area or area of each pole. What about no load terminal voltage? That is 559.2. Why is it no load terminal voltage? Because under no load, terminal voltage is equal to induced EMF. Next concept, let us take a look at the electromechanical energy conversion. So this concept was asked in a recent year. Here what you have to remember is, you have to remember the concept of mechanical energy. Now what is mechanical energy? It is given by integral I into d lambda. Lambda is basically flux linkage. Okay. And remember, whenever we want to find out mechanical energy, we will take as lambda as constant. Okay. Now, there is another concept of co-energy. Co-energy is basically lambda into di. Okay. That is basically your co-energy. So, the force that exists in order to reduce the air gap is equal to dW by dg, where g is your air gap. So this concept is very necessary, that first you find out the stored energy in the system and then you find out the force acting in the system by taking the derivative of stored energy or the mechanical energy. Stored energy can be determined in another ways, like half Li square. That is another way of finding the stored energy. If you differentiate it with the respect to air gap, you will get the force that acts in the system. Now let us take a look at the problem that was asked. Here lambda is given as under root I by g, which means I is equal to lambda square g square. Now for finding the energy, first we have to calculate the work done or energy stored. That is integral I into d lambda. Lambda square g square into d lambda, which means g square lambda cube by 3. Now as I told you, force is nothing but derivative of stored energy with respect to distance, 2 lambda cube into g into 3. Now lambda can be written in terms of I. So it will be 2 I to the power 3 by 2 3 g square. I have substituted this relation. I know the value of I by 3 into 0.01 because 10 centimeter is 0.1 meter. So this will come out to be 188.56 Newton. So you have to deal with such kind of problems in this manner. First find stored energy in the system and then differentiate it with respect to air gap. The next category comes to be different types of generators that can be designed, different configurations. So overall, how many configurations are there? First one is called as separately excited. Then the next one is called as self-excited. In self-excited, there are various categories: shunt, then series, then compound. Compound is basically combination of shunt and series. So, first let us talk about separately excited generator. In separately excited generator, the field winding is supplied from a different source. So, what you can do is, you can assume that flux remains constant. So, wherever you go through the term called as separately excited, the first thing that must pop up into your mind is that the flux will remain constant. Now, let us see what it is talking about. A separately excited generator. So, in separately excited, what you will show? Armature resistance, induced EMF, and just the terminal voltage. There will be no concept of field because field is excited by a separate source. Okay. So what it is saying? A separately excited generator when running at 1200 RPM supplies 200 ampere. Now it is saying IA as 200 ampere because here the current supplied to load is IA. Terminal voltage is 125 volt. And the load has a constant resistance, which means load resistance is voltage by current, which means it will be 0.625 ohm. Now what will be the current when the speed is dropped to 1000 RPM if field current is unaltered, that is flux is constant, armature resistance is given to us, brush drop is given. So when you change the speed, we just now saw EMF is proportional to flux into speed. That means EMF will change as you change the speed. Which means whenever we talk about speed, the first thing that must come to mind is EMF. So let us calculate EMF. 125 plus armature resistance is 0.04 into current is 200. So how much will this come out to be? Plus 2 volt more we will take. Why 2 volt? For the brush voltage drop. 135 volt. Now we have changed the speed to 1000 RPM. Since flux is constant, I can say EMF is proportional to speed. E2 by E1 is N2 by N1. So E2 is E1 into new speed is 1000 RPM. Earlier it was 1200 RPM. So it will come out to be, how much will it come out to be? 112.5 volt. Now it is asking us the current. Now I know that EMF is there and the load has a constant resistance RL. So what will be the current? Simply by KVL I can say IA will be EA by RA plus RL. Now once I know about this current, I can write down IA is equal to 112.5 by RA. RA is how much? 0.04. RL is 0.625. So this will come out to be 166.16 ampere. So that will be the load current if you change the speed. So remember, whenever a constant resistive load is given to you, you have to first calculate the load resistance. Moving forward, let us look at another problem based on separately excited generator. Here it is saying 10 kilowatt 6-pole DC generator develops a EMF of 200 volt at 1500 RPM. So EMF is given to me and the speed is given to me. Now it is saying lap connected winding, which means number of parallel paths is equal to pole, that is 6. Flux density is given to me 0.9 Tesla. Length and the diameter are given to me. So length is 0.25 meter. Radius will be half of diameter, 0.1 meter. We need to first calculate flux per pole. Now I know flux is equal to B into area, which means flux per pole is B into area per pole, which means it is 0.9. Area will be how much? 2 into pi into r into L. Number of poles are 6. So how much will this come out to be flux per pole? 0.0235 Weber. Okay. So remember, in EMF equation, whenever we put the flux per pole. Next, it is asking about active conductors in armature, that is Z. So think about it. Where do we see Z? Z is only seen in the equations that involve induced EMF. So induced EMF is nothing but phi n Z by 60. Why I am not writing P by A? Because it is lap winding, P is equal to A, it will get cancelled out. Now we know EMF 200 is equal to 0.0235 1500 RPM. Z we do not know, by 60, which means Z will come out to be almost 340, which means we have 340 conductors in the armature. Next, it is asking us about the developed torque. So see, whenever we talk about an electrical machine, there are two types of torque: developed torque and shaft torque. Now, the difference between these two, developed and shaft, is basically lost torque. Lost torque corresponds to the friction and windage losses that occur in any kind of rotating machine. What is meant by developed torque? It corresponds to developed power, which is the power being converted from electrical to mechanical or vice versa. So developed torque in a DC machine is given by phi Ia Z by 2 pi P by A. So remember, it is proportional to flux into Ia. These concepts are far more helpful when we will talk about DC motor rather than DC generator. So if you wish to find out developed torque, it is 0.0235. Now what is the current? 50 ampere. Z is 340 by 2 pi. P by A will be 1. So this comes out to be 63.58 Newton meter. So that will be the developed torque. If you wish to calculate developed power, it will be simply developed torque into omega, where omega is 2 pi into n by 60. So it is the angular speed in radian per second. So remember this concept about the developed torque. Next category, let us look at shunt generator. It is saying a belt driven 60 kilowatt shunt wound DC generator running at 500 RPM is supplying full load to a bus bar at 200 volt. At what speed it will run if the belt breaks, machine continues to run taking 5 kilowatt from the bus bar. Armature and field resistances are given. So remember, in a shunt generator, till the terminal voltage is constant, you can assume flux to be constant. What is the equivalent circuit? First we have field resistance. It is connected in shunt with the machine. Then we have armature resistance, induced EMF and terminal voltage. Here we have armature current IA, field current IF, load current IL. IL will be equal to IA minus IF. This KCL equation is actually quite important because this equation changes when we talk about generator and motor, so kindly keep this in mind. Now it is saying neglect armature reaction, which means flux can be taken as constant. Why? Because armature reaction has demagnetizing effect, so it tends to reduce the flux, but you can neglect that effect. Now it is supplying full load to a bus bar at 200 volt. Full load means the rated power. So what will be the load current? 60 into 10 to the power 3 by 200. So this will come out to be 300 ampere. Now remember, this is load current and not the armature current. Field current will be how much? Terminal voltage by resistance, that is 2 ampere. So what will be armature current? Sum of these two, 302 ampere. Now what will be the EMF? The EMF will be 200 plus IA 302 into RA 0.1, that is 230.2. But we have to add 2 volt as the brush drop. So plus 2, so it will be 232.2 volt. Now I know about the generated EMF, that is 232.2. Now it is saying the belt breaks. The belt is basically used to connect the generator to the prime mover. If belt breaks, basically it means we are removing the prime mover. If you remove the prime mover, then what happens? The machine will start acting as a generator and it draws 5000 watt from the supply. So we can calculate armature current, load current. 5000 watt by 200, I am assuming terminal voltage as constant, 25 ampere. Now field current shall remain same because VT is same, 2 ampere. Now as I told, the condition or the KCL equation reverses between generator and motor, means IA will be IL minus IF, not the sum. That is 23 ampere. Which means if we calculate motor EMF, it will be terminal voltage, that is 200 minus 23 into 0.1. So how much will this come out to be? You have to subtract 2 also. Why? For brush drop, 195.7 volt. Now as we know the flux is constant, it means EMF is proportional to just the speed, or I can say motor EMF by generator EMF is equal to motor speed by generator speed, which means speed of motor is 195.7 divided by 232.2 into generator speed is 500 RPM. So this will come out to be 421.4 RPM. Okay. So that is how you do such kind of problem where a generator is converted to motor. Again, I am telling you the golden rule that whenever speed changes, first thing that you should try and find out is the EMF. Let us look at another problem based on shunt generator. A generator delivers a current of 50 ampere at 200 volt to a load of constant resistance while running at 1000 RPM. Its armature circuit resistance is 0.5 ohm and that of field winding is 50 ohm. Find the load current in case speed of DC generator falls to 800 RPM but field current is held constant at previous value. Neglect armature reaction. A similar kind of problem we just now saw earlier. So let me make a modification here. So I will change the load from constant resistance to, let us say, a load of variable resistance or a non-linear resistor where V is equal to I square. That is basically your characteristic of the load. Now it is saying a generator is delivering 50 ampere current at 200 volt, which means if it is shunt generator, what is IL? 50 ampere. What about IF? 200 by 50, that is 4 ampere. So what about IA? By KCL it will be 54 ampere. Now here I can calculate EMF. If you wish to calculate EMF, how much will it be? EMF will be VT 200 plus IA 54 into RA 0.5, that is 227 volt. Now it is saying field current is held constant, which means flux is constant, so EMF is proportional to speed, which means if we change the speed, EMF will change by the same proportion. So E2 will be E1 into N2 by N1. So it will become 181.6 volt. Now we know the new induced EMF. What about terminal voltage? 181.6 EMF minus I into RA 0.5. Now we know it will be equal to load voltage, which is actually equal to I square. So we get a quadratic equation. So what we can do is, we can find out the current by solving this equation. It comes out to be, this will actually be basically IL. So it will come out to be how much? 13 point, sorry, it will be, so one thing we have to do here is, basically we get 181.6. So it will be 181.6 minus minus IA into RA. RA is how much? 0.5 is equal to IL square. Now IL is how much? IL is basically IA minus IF. IF is 4. It is saying field current held constant. So we will get a quadratic equation from here, that IA square, okay, minus 8 IA plus 0.5 minus 7.5 IA, then how much? It will be 16 minus 181.6. So once you get this quadratic equation, you can calculate the value of IA, and once you calculate IA, you can calculate IL as IA minus IF. So that is how you deal with such kind of problems. Okay, this equation you can solve at your own end. I am not finding the value, you can find that yourself. Is it fine? So we can deal with any kind of load in generators, not necessarily a constant resistive load. Next category, let us look at a compound generator. So compound generator has basically two configurations. One is long shunt, one is short shunt. Since the first problem is about long shunt, let me show you the equivalent circuit. It is like this. R shunt, first the series winding is connected in series with the armature, and then we connect the shunt. So that is how we perform a long shunt. Okay, it is nothing much different from a shunt generator, except for the fact that armature resistance is replaced by armature resistance in series with the series winding resistance. So here you can calculate IF. So what will be IF? Terminal voltage, that is 220, by field winding resistance, that is 50, shunt winding resistance 4.4 ampere. Okay, now what is load? Load is 60 watt, 100 lamps, that is 6 kilowatt. Based on that I can calculate IL, 6000 by 220. So what will be the value of IL? 27.27 ampere. Now since it much more or less behaves like a shunt machine, IA will be IL plus IF. If you add these two things, we will get 31.672. Now once we have armature current, I can find out EMF. It will be terminal voltage 220 plus 31.672. Now here we have two resistors in series, RA and RSC. So the total will be 0.4. So this will come out to be 232.668 volt. So that is what will be the induced EMF. Okay. Now let us look at what is the model for a short shunt machine. In case of short shunt, the circuit is somewhat like this. This will be R shunt, RA, EA, R series. So first the shunt winding will be connected across the armature and then the series resistance. So we just now calculated IL, it was 27.27. That will remain same. So let me calculate the voltage across the field winding, that is VF. This is IL, this is VT. So field winding voltage is terminal voltage plus IL into R series. VT is 220 plus 27.27 into R series. R series is how much? 0.15. So how much will this come out to be? 224.09 volt. Based on that, we can calculate field current. 224.09 by field resistance is 50. So it will be 4.4818 ampere. Again, just like a shunt machine, IA will be IL plus IF. 27.27 plus 4.4818, which means IA will be 31.7518 ampere. Once we have gotten the armature current, we can find out the induced EMF. But for induced EMF, we cannot directly use the terminal voltage. Rather, we have to use the voltage across the armature, which was 224.09 plus armature current was 31.7518 into armature resistance is 0.25. So this will come out to be 232.02 volt. Okay. So in case of compound machine, if you have drawn the equivalent circuit, the problem is reduced to solving just the case of a circuit. Okay, you just have to solve a circuit and you will get the answer. The next machine is your series generator. In series generator, the winding is connected or the field winding is connected in series with armature, which means armature current is equal to field current. So what will be the equivalent circuit? This will be our induced EMF, armature resistance, series resistance, armature current and terminal voltage. Now what is the basic use of such kind of generator is, they are used as a booster to reduce the voltage drop in a line. So let us see this application by means of a problem. A series generator having external characteristic which is a straight line through 0 to 50 volt at 200 ampere. External characteristics means VT versus IL. It means the terminal voltage is 200 at 200 ampere is 50 volt. Now it is connected as a booster between a station bus bar and a feeder of 0.3 ohm resistance. Suppose this is a bus. Here we will connect a DC generator and this shall be a feeder which has a resistance of 0.3 ohm. Now we have to find the voltage between these 2 points, that is between the far end of feeder and the bus bar, at a current of 160 ampere. Now it is saying the external characteristics are straight line, which means what is the terminal voltage at 160 ampere? The slope is 50 by 200 into 160, that is 40 volt. Which means if it carries a current of 160 ampere, the voltage across the DC series generator is 40 volt. So what is total voltage? 40 minus current is 160 into resistance 0.3, that is the resistance of feeder, that is minus 8 volt. So see, if we hadn't placed a series generator, the voltage drop would be across the feeder, that is 48 volt. But after placing the feed booster, the voltage drop is reduced to 8 volt. So that is the basic use of DC series generator. The last category of problems that can be asked from a generator is parallel operation. Now why two generators or any two machines are connected in parallel? So that they can handle a higher load as compared to their original loads. So in parallel operation, you do not have to do anything, just consist of or consider it as two circuits that are connected in parallel and then apply the network analysis. Let me show you here. It is saying two DC shunt generator operating in parallel share a load current of 300 ampere, which means the sum of their load current is 300 ampere. Each generator has armature resistance of 0.2 ohm, field resistance of 150 ohm. Now we also know the no load generated EMF. So what it is telling us, this is one generator. Similarly, we have another generator like this, and here we have load. This is ILA, ILB. The load current here is 300. So this is 0.2, 0.2, 150, 150. The EMF of first machine is 275, the second one is 270. Now, since these are shunt machine, which means ILA is equal to IAA minus field current, ILB is equal to IAB minus again field current. Now field current will be same in both the cases. Why? Because field resistance for both machines is same and both are connected in parallel, which means their voltage is also same. So now what I can do is, if the terminal voltage is V, so how will V be defined? EMF minus IA. IAA will be ILA plus IF. How to find IF? Terminal voltage by 150 into resistance is 0.2. Similarly, V for second generator, 270 minus ILB. IF will be same, terminal voltage by 150 into 0.2. So now if you see, we have three variables, the load currents and the terminal voltage V. If you solve these three equations, what you will get is ILA will come out to be 162.5 ampere. ILB will come out to be 137.5 ampere and terminal voltage will come out to be 242.18 volt. Okay. So that is how you can deal with any problem of parallel operation. First draw the equivalent circuit and then apply network analysis, basically KCL and KVL, to determine the desired parameter. So such kind of questions can be framed in GATE examination from DC generator, though the questions from DC motor are far more common. Okay. So we'll look at the problems based on DC motor later on, but this is the sufficient what you need to know about the DC generator.